So we've seen in the previous couple of lectures how we can generate the lift on our aircraft, and so we can get the aircraft to fly. What's now interesting is to look at how we get the aircraft to fly efficiently and how we can get the best gliding performance out of our aircraft. Now, if we consider a powered aircraft, in cruising flight we have a balance of forces. Our thrust force equals our drag force, and our lift force equals our weight. If we have an imbalance in these forces, then the aircraft will accelerate. So let's think that the thrust is increased. Now if the thrust increases, then our thrust is bigger than our drag. The aircraft will accelerate, go faster, until the drag force increases such that we reach a balance again of thrust equals drag, and the aircraft will fly at constant speed. If we reduce the thrust, then the aircraft will start slowing down, and it will continue slowing down until again we hit this balance of our thrust equals to our drag. Now we can fly in steady gliding flight at constant speed, and therefore we must have a balance of forces. But we don't have a thrust. So in a glider you would think, well, we have no thrust, all we have is drag, therefore the aircraft should keep slowing down until it gradually stops. So where in a glider do we generate this thrust force to balance the drag? In a glider we're always descending, and we're descending at a glide angle given here by the symbol gamma. Now because we're descending at an angle to the horizontal, we have a component of our weight acting in the direction of flight. Now that component of the weight in the direction of flight balances the drag force, and if we're flying in steady gliding flight, the speed is constant, then we're at an angle such that the component of our weight equals the drag being generated by the airframe. And when we're in this steady gliding flight, we can estimate what the glide angle of the aircraft is by inspection. And what we see by inspection here, we can see that the glide angle is equal to the component of the weight in the direction of motion divided by the lift force, and that gives us our glide angle. Now, what is our component of our weight in the direction of flight? It's not easy to discern, but what we would recognize is that when we're in steady gliding flight, that component of the weight in the direction of flight is equal to the drag force, because that essentially the thrust being generated is equal to the drag, and therefore our speed is constant. So we can substitute into our little equation for the glide angle the drag, and so the glide angle is actually equal to the drag force being generated by our aircraft divided by the lift. Now for the minimum glide angle, we therefore want the minimum drag to lift ratio, and saying the minimum drag to lift ratio is the same as saying the maximum lift to drag ratio. Therefore, for the minimum glide angle, we want the maximum ratio of lift to drag. Now why do we want a minimum glide angle? Well, let's think of us flying along, and we're flying along at a reasonably large gliding angle. Now from a given height, depending on our glide angle, will give us the distance that we can fly before we essentially hit the ground. For a given height, the glide angle gives us the range that our aircraft can fly, and therefore for the maximum range that our aircraft can fly from a given height, we want the glide angle to be as small as possible. And therefore if we want the glide angle to be as small as possible, from the previous slide what we're actually after is the maximum lift to drag ratio. Therefore for maximum range we fly at the maximum lift to drag ratio, and hence the minimum glide angle. The other thing our lift to drag ratio shows us is that it actually tells us how far we can go from a given height. say I have a maximum lift to drag ratio of 50 and I'm at a height of say 1 kilometer, I could fly forward 50 kilometers for a loss of height of 1 kilometer, and therefore flying at my maximum lift to drag ratio gives me my best range. And if we look at the speed of the glider and the rate of sink, we can also see that the glide angle is dependent on the speed of the aircraft and the rate of sink. And to fly for maximum endurance, what we actually want to do is to fly at the minimum sink rate for the aircraft. Now what we notice here is that the glide angle that we use for maximum range is not the same as the glide angle we would need to have for maximum endurance. And what we would find is that the speed at which we fly for maximum endurance is about 76% of the speed that we would fly for maximum range. Now we can see this data plotted in our pilot's handbooks as what's known as speed polars. And what a speed polar does, it plots the rate of descent, in this case in meters per second, against the airspeed of the aircraft, in this case in kilometers per hour. Now what information can we get from these speed polars? Well, one of the things we can get from them is the minimum rate of descent. So here's my rate of descent, and if I look across, I can find the peak of the curve, and where I find the peak of the curve, that is my minimum rate of descent. I can pick that up. It looks just above 0.5 meters per second for that aircraft. I could also, off of these curves, get the lift to drag ratio. And the way we get the lift to drag ratio and the speed to fly for the lift to drag ratio is to plot a line from the origin, 0 speed, 0 sink, to a tangent on the surface of the curve of the speed polar. And if I draw that tangent, the slope of the line gives me the lift to drag ratio. So here this is an ASK 21, and what we see is that the slope of the line drawn from the origin to be a tangent to the surface is 34. So for an ASK 21, glide ratio, lift to drag ratio is 34. And the speed to fly for that ideal lift to drag ratio for maximum range would be at, well, looking here, at about 90 kilometers per hour. Notice how with the ASG 29 we can have water in the wings, and so we have two different wing loadings, which is the weight of the aircraft divided by the wing area. And what we see here is that when we have a low wing loading, that's no water in the wings, our rate of descent is much less than when the aircraft has water in the wings. But if we look at the lift to drag ratio, then what we will see is that the lift to drag ratio for the ASG 29 is, if I look at the slope of the line, is 50, and irrespective of whether the aircraft has no water in the wings, low wing loading, or water in the wings and high wing loading, it hasn't affected the lift to drag ratio of the aircraft. It still is 50 to 1. But what I do notice is that the speed at which you want to fly with low wing loading and high wing loading are different. And that's the benefit of putting water in the wings. You get the same lift to drag ratio, but what you get is that lift to drag ratio at a much higher speed.